Outbreak of the deadly virus is spreading rapidly. Unprecedented threat requires a worldwide quarantine.
Marge, kids, everything's gonna be just fine.
Yo, listen up, I got a story about a teacher, Mr. Wright, yeah, he's a biology creature. In the classroom, he's spitting knowledge like a preacher. With his lab coat on, he's the lyrical feature. He's got test tubes and beakers mixing up that potion, teaching us about cells and the process of mitosis.
Hi Year 11s, this is going to be the fourth video in our infectious diseases unit. This PowerPoint's going to be a little bit longer than some of the others. We're looking at preventing infection and we're going to be introducing a few new terms here because of that. So starting off, we're going to start with a term called specific immunity. Now specific immunity is part of your immune system that can be acquired either passively or actively, and either naturally or artificial. Now we'll go through some examples of that so they understand what that means. So for example, if I was to get specific immunity naturally and actively, I would be acquiring immunity through actually my immune system responding to a pathogen entering my body, making me sick, and my immune system fights off that infection and learns how to fight and remembers that essentially that pathogen so it can fight it in future. So my immune system is boosted up because I know how to fight that infection, and I've learnt that through physically fighting off that infection once before. So it's naturally and actively. On the other hand, if I'm talking about naturally passively, talking about fetuses or newborn babies who haven't experienced illnesses or can't get sick themselves, the antibodies they get are naturally from their mother. But they're actually, the child themselves isn't getting sick. They're getting those antibodies directly from the mum, either through her placenta before they're born, or through the milk they're drinking, through mammary glands, through breastfeeding. On the other hand, we can artificially receive specific immunity. One, maybe in an active form of obtaining specific immunity artificially, would be through vaccines. We're exposing our body to a foreign material, initiating a specific response specific to that pathogen in the vaccine without getting sick. On the other hand, if we wanted to acquire specific immunity artificially and passively, we'd be talking about taking something like antivenom, where we're giving ourselves antibodies introduced, or lymphocytes introduced through that antivenom. What we're going to focus on a little bit more, though, here is really pushing with vaccines, so how vaccines work and what vaccines are. So vaccines, the job of them is to stimulate the production of antibodies and lymphocytes, which are a type of memory cells in our body, without causing illness. So to do that, generally vaccines contain one of the following things: either an inactive form of the pathogen that has been weakened, or a less active form of the pathogen that's less likely to cause disease, just the antigens, so the antibody generators that are attached to the pathogen, or an inactive form of the toxin released by the pathogen. A few typos there. Let me just fix that one up and change the word to the word toxin. So an inactive form of the toxin released by the pathogen. So essentially, we're trying to get a response without making you sick in all those situations. How does that work, though? How does giving one of those, a vaccine with one of those four things in it, how does that work? Well, start with, it initiates your primary immune response to the pathogen. So that means your body's trying to kill that pathogen that's found in the vaccine. So they produce what's known as memory T and B cells. We're going to talk about these a little bit later. For now, we just know we're creating what's known as memory T and B cells. Once your body has created those, if you're ever exposed to that pathogen again, you get a secondary response. Now that secondary response is much faster and more effective at neutralizing or killing off the pathogen before symptoms occur compared to that primary response. So by initiating that primary response from the vaccine, it makes that secondary response much faster. Now in terms of vaccines, some vaccines will protect individuals for life. Others will require boosters, which is an extra dose of a vaccine after the first dose. How frequently you need those is going to be based on the virus or the immunization that we're talking about. So ones we've talked about in class, for example, tetanus is given roughly every 10 years because after 10 years your memory B and T cells have probably died out, and if you've not been exposed to that virus, you need to be re-exposed. There is a little video about this, why vaccines work. This will be on Doing Science Right for you to watch. I'm not going to play it during this video. We might play it in class. If not, that's something you can watch on Doing Science Right. Pushing that a little bit further, why this might not always work for preventing infections is that sometimes pathogens change. And they change because of something known as antigenic drift or antigenic shift. So these are sort of adaptations as such. Antigenic drift is essentially when a pathogen constantly changes the antigens on its surface, giving us new strains of pathogens, making it hard to immunize a patient with one vaccine because the strain is constantly changing. Now, the most common example of this is influenza. You need an influenza shot every year because each year we're looking at new strains of the flu, generally that have come from the other side of the world and now migrating to us in winter. So with that antigenic drift, happening so fast with influenza, we have that immunization every year to protect us. You could sort of say the same with COVID. We've had so many variations, and the antigens are changing slightly, but with COVID, slightly different because the old immunizations are still sort of protecting us as well. Antigenic shift, on the other hand, is when two viruses infect one host at the same time. Generally, it has to be an animal virus and a human virus. And what happens is those two viruses combine and become packaged into one virus, which is unrecognized by our immune system, and we essentially create a new mutated virus mixing of two together. Another thing that pathogens are constantly adapting to is antibiotics. Now, these are antibiotics. We've talked about this a little bit in class. Antibiotics are chemical compounds that we use to inhibit the growth of bacteria inside a host. So there's 8 different classes of antibiotics. You'll probably do an experiment with these with a antibiotic ring disc and E. coli. And each class of those antibiotics inhibits the growth of bacteria by stopping a specific process. That could be the formation of cell walls, creating DNA or proteins. What they don't do, antibiotics, is inhibit the growth of viruses, and hence they aren't good for treating viral infections, but unfortunately doctors do sometimes prescribe them inappropriately to treat viral infections. That overuse, or this inappropriate use of antibiotics, has led us to what we call antibiotic-resistant bacteria. Now that occurs because naturally bacteria and all organisms that have DNA have mutations that occur over time. And the DNA that codes for a protein is based on those mutations. If a mutation happens that impacts how a protein's created, it's going to change the protein that's created. So essentially, we've had random mutations that occur that allow bacteria to produce proteins that can resist the action of antibiotics. Now, that's going to happen naturally anyway. But they know it's successful if we have antibiotics naturally in our environment, such as with livestock, etc., being used to help their growth and prevent them getting sick. If that antibiotic is there without them being sick, the bacteria are producing these proteins, and hey, we're not dying because we've made this protein, so natural selection works and those bacteria survive while others don't. And hence we end up with this stronger strain of bacteria because they haven't been killed off by the antibiotics around. Only a little bit left of this PowerPoint. We're going to push ahead for one video. So preventing infections. So from the around 1900s and 1980s, we had a drastic reduction of deaths caused by infectious diseases because of antibiotics, vaccines, and because of increased public health. But since 1980, if we look at trends, and we'll look at these in class a little bit, we've started to have the number of deaths caused by infectious diseases creep back up. And that's because of what we call emerging infectious diseases, as well as the re-emergence of other diseases. So when we say an emerging infectious disease, this is a disease that's not occurred in humans before. So an example of that would be COVID. But a re-emerging infectious disease is one that hasn't posed a health risk to a large population for some time, but they're returning and causing major health concerns. So we watched the video previously on how measles made a comeback, and measles would be a good example of a re-emerging infectious disease. Some other examples of these. So if we're looking at emerging diseases, so new diseases that we haven't seen before, ones that are still going, H1N1 influenza, which is swine flu, the avian influenza, which is bird flu, HIV, Ebola, cholera, and obviously now COVID as well. Re-emerging diseases, TB, tuberculosis, whooping cough, malaria, yellow fever, etc. Now the question is, if we've essentially beaten a lot of these diseases and we've got improved public health and we've started to have decreased deaths from these right up into the 1980s, why have these re-emerging diseases started to re-emerge? And the simple being is there's a number of reasons. One, international travel, and we talked about this before. International travel is easier than ever, it's cheaper than ever, we're spreading around. People that haven't been exposed to these pathogens before now can be exposed, and hence there's more people to be infected. So we see some of these viruses re-emerge. We've got a decrease in the quality of water, with more and more countries having poorer sanitation levels or reductions in the income of the country. We're seeing lower quality water and people getting sicker because of that. We're seeing pathogens obtain drug resistance or antibiotic resistance because we've been overusing antibiotics. We've got pathogens that are mutating, so they're now not treated by the old ways that we used to treat them. And we also have this uprising of fake news, which is essentially telling people that vaccines aren't safe, they cause autism, which is wrong, and hence we've got people failing to vaccinate their children and themselves, which is meaning our herd immunity is dropping, and we've talked about that before. Now, how do we classify diseases? So, how can we change a disease from endemic, which is expected, to epidemic, which is unexpected? Okay, that could be because we've had disease mutating because of antibiotic resistance. We could have had antigenic drift or shift. We could have had mutations from pathogens being unable. They're made actually now able to produce new toxins which we don't have immunity to. The immunity level could be dropping because of the lack of faith in vaccines, and you could be having more third world countries with less sanitation. But despite all this, there is still ways that we can control these infections, and that's through identifying, tracking and stopping outbreaks of particular pathogen, and there's different measures that we can do that. So one, controlling carriers of disease. So disease are often spread by vectors, we've talked about that before, and vectors can be controlled through insecticides, killing the vector, or vaccinating domestic animals from those diseases so those diseases can't be spread. We could kill the pathogen. We could use vaccines, we could use antibiotics, antivirals, etc. to kill off pathogens. We could use disinfectants and antiseptics to kill pathogens on the skin and surfaces so that those pathogens aren't actually there to get us sick. We could make sure that the vaccination programs are working properly and we have a good immune response, and there's there's herd immunity in the population, because populations with herd immunity are less likely to experience an epidemic. On the other hand, overcrowded, undeveloped countries see more infectious diseases because they don't have clean water, they don't have sanitation, and they don't have appropriate vaccination programs. Lastly, and one that you're probably all very familiar with because of COVID, is quarantining carriers, where if someone is sick, we quarantine them, or this can be with animals too, until they're better, meaning the pathogen can't be passed on from those people. That was a lot of information in that video. We will go through it in class. Feel free to ask me questions in BioHelp or in the lessons if you want to go over any of this in more depth.